We've already learned that concentration and temperature changes will affect rates. The collision model is a method for explaining both why and how concentration and temperature changes will affect the rates. And this model has a couple of underlying concepts. So the first one is straightforward, and we've already discussed it when we talked about factors affecting rates. Molecules need to collide in order to react. So the reactant A must collide with reactant B in order for this reaction to occur. And clearly, as concentration increases, the odds of those molecules colliding is going to go up. The second underlying concept in the collision model is that collisions have to happen in the correct orientation for the reaction to happen. So we'll look at an example of chlorine reacting with NaCl. Notice that one of the products is Cl2. In order for this reaction to happen, the chlorine atom must collide with the chlorine part of the NaCl molecule. So we'll look at two different ways in which the chlorine atom can collide with the NaCl molecule. I've omitted most of the electrons here for clarity, but in the first example you can see when the reactants collide, the chlorines will collide together. In the second example, when the reactants collide, the chlorine will impact against the oxygen and no reaction will occur. So again, the collision model implies that the right types of collision need to happen. And the odds of the right types of collisions occurring are going to increase as the concentration increases, simply because there are more reagent molecules and particles available to potentially collide. The third underlying concept for the collision model is that the collision energy needs to exceed the activation energy. And that is the energy that's needed to start a chemical reaction, and it's given the symbol EA. So we're going to look at a pretty simple example of A going to B. And our example will be a rearrangement of a molecule. So in this example, the nitrogen and carbons are going to switch place, and that's the only thing that happens in this chemical reaction. And we'll draw what's known as a reaction coordinate diagram or a potential energy profile. It can be given kind of different names. This type of diagram shows the potential energy of the system as the reaction progresses from left to right or from reactants to products. So you always start at the left-hand side with your reactants. In this example, our reactants start with a certain amount of energy. There's a large increase in potential energy as the reaction progresses, and then towards the end, the products form, and they're in a lower potential energy state than the reactants. So what's happening that causes that large increase in potential energy in the middle? So it happens because a reactant doesn't immediately transform into our product. It has to move through a transition state along the way. So we see something like this happening. And as this rotation occurs, the chemical gains potential energy. The final position, the transition state, has the highest potential energy. And after this point in the rearrangement, the potential energy is going to start to drop as the structure approaches the structure of the products. So at this point, halfway through the rearrangement, we've drawn the first half of that reaction coordinate diagram. And right at the top of that curve is our transition state. And then the rearrangement continues and the product forms. And the activation energy is the difference in energy between the transition state and the starting potential energy. And this activation energy is going to be related to temperature. And it's related to temperature using what's known as the Arrhenius equation. So K is equal to A, which is a frequency factor constant, times E raised to the power of negative activation energy divided by RT. And this R is the same R as we saw in the gas law section. And while I won't actually ever ask you to use the Arrhenius equation, you can look at it and take away a couple of points, which is that as temperature increases, K increases, assuming the activation energy stays the same. And if K increases, the rate increases.